Today's musicians are frequently on a tight schedule. The lead singer of a band might have singing lessons in the morning, while an accompanying pianist may have their own shows at night. Oftentimes, the singer in this situation would still prefer to practice with live accompaniment rather than turning to digital-sounding MIDI files, but they have no way of finding an alternative pianist. Player pianos that can play without humans could be an option, but these are not portable and often also very costly. Today's musicians are also on a tight budget, or at least they are when they're first starting out their musical careers. Because of this, many amateur artists may not be able to afford hiring professional piano accompanists to perform alongside for their shows. We recognize these plights of musicians across the globe and in turn present to you the accompanyBot. Our affordable prototype demonstrates the ability to have an automated accompanist at your fingertips. It works by reading real music notated scores into data structures and playing the corresponding notes by striking the keys with actuated solenoids.
Our overall system can be broken up into three main subsystems. The first subsystem is our local application, which runs on the user's computer and provides a graphical interface to interact with the accompanyBot. On this application, users upload pictures or PDFs of their sheet music, which is parsed by an optical music recognition software into an XML file. This is the file that is transmitted downstream for scheduling the notes. User actions for playing, pausing, changing the tempo, and jumping to different measures are communicated serially via a USB cable to the second part of our system, which is the signal coordination and note scheduler. This subsystem consists of a Raspberry Pi 4, which runs the main control function to convert the received file into voltage level outputs on the GPIO pins. An Arduino Uno aids in the USB to UART conversion between the computer and the Raspberry Pi for the serial commands. However, we opted to use secure copying via the SSH protocol to copy the file itself because of the reduced latency when the transfer was done over a wireless network. The final subsystem is the physical interface, which converts the electrical signals outputted by the Raspberry Pi into actual key presses on the piano. This is done by connecting the GPIO pins to the gates of the 12 switching transistors. Each transistor is placed in series with a solenoid, such that when the transistor is on, the corresponding solenoid will draw current and actuate the shaft to press down on its respective key.
While planning out the local application, we needed a way for uploaded music scores to get read into XML. We researched many different optical music recognition solutions and ultimately selected Audiveris for our needs. It has challenges with integration, but works very well and has a functional documentation for how to use it through a command line interface. Take the Charlie Brown theme. With Audiveris, the machine learning solution analyzes the PDF or PNG in its entirety. For this reason, the scores should be as crisp as possible. Audiveris works by first discerning smaller items like where the note heads are or measure markings. It then proceeds to break down the score in an organized fashion, first looking at the different parts and clefs, as well as the time signature of the piece. It then groups together the notes and chords, as well as rests in each of the measures into the XML. The layout of the XML is much like the HTML format of a website, with descriptive tags enclosing the extracted data. This makes it possible to process the music information from the XML into Python data structures using MIT's Music21 library.
The note scheduling algorithm is done on the Raspberry Pi each time a new file is uploaded by the user. As Rahul mentioned, we are using Music21 to parse the XML file. The text on the left shows an example of a Music21 output for the notes in the top right. The Music21 library allows us to access a list of notes in the piece, which we iterate through and convert into signals on the digital GPIO pins that are mapped to a different key. As we encounter new notes in the piece, we get their duration so that we can schedule a downpress at the start of the note and a lifting up at the end of the note. We then find their measure number and offset within the measure and use them as keys in the nested dictionary structure shown on the right. Music21 also enables us to extract information about the piece's tempo and time signature that allows us to compute the duration of one measure, which we pass back to our main control. In the main control function, there's a continuous loop that checks for user inputs to play or pause. When the Raspberry Pi receives a play, the program records the starting time and starting measure, and then loops, using the Raspberry Pi's system time to determine when the measure is and what needs to be played. Based on the measure, the Raspberry Pi reads the dictionary of notes and sends the correct signals to the GPIO pins, which will control the piano key presses.
The solenoid actuation is controlled primarily by the Raspberry Pi's GPIO pins. High and low signals are sent across the GPIO pins, causing the MOSFET to turn on and off. Since the solenoids are in series with the MOSFETs, they will receive some current across their terminals. Once the solenoids receive this current, they will actuate, pressing down on the piano keys below. Additionally, there are diodes placed in parallel with each solenoid as a safety mechanism to prevent any flyback voltage due to the current being cut off from the solenoid. Without these diodes, the solenoid's flyback voltage could easily damage the other devices connected to the system, like the Raspberry Pi. The last major component to our system is the chassis. The chassis is made out of 4 major components. These components include the base, where all the solenoids are placed on top of and secured in place, the walls that house all the components, the top so that no one can stick their fingers inside, and the support beam on the bottom that helps keep the solenoid suspended over the piano keys. In addition to these 4 major components, there are other noteworthy design choices, including the rectangular feature that juts out from the back of the chassis base, which also helps support the chassis and suspend the solenoids over the piano keys, and the cutout in the top so that GPIO and power cables can be routed into the chassis.
This is the accompanyBot application that users interact with directly. Here we can insert the music file, which then goes to the optical music recognition stage and allows us to begin playing the accompanyBot at octave 3. So that was in tempo of 120 BPM. Oops. We can lower the tempo to 90 BPM to see a drastic change in the speed of the accompanyBot's playing. Let's go back to measure 0. That's the accompanyBot.
To conclude, throughout the process of planning, designing, and integrating our project over the course of the semester, we have learned a couple lessons. First being that integration takes a lot of time and to plan accordingly. 3 weeks of slack time was ultimately too little as we used up all of it integrating our subsystems into one cohesive product. The other major lesson that we learned was to modularize and prototype systems that take a long time to make or fabricate. For example, 3D printing the chassis in one go would have taken well over a day, so instead, we broke down the design into 4 major parts as described earlier. This helped to work out kinks in the design and get it just right while also not waiting over a day for one iteration to complete. Going forward in school and the workplace, when we have large projects such as this one, we will take these lessons into consideration. Now, to end the video, we would like to give a special thank you to our TA Alex and Professor Sullivan for all their help this semester.